Greetings everyone! As we reach the final week of our course, today's topic centers on discussing about the sustainability and environmental consideration linked to 3D concrete printing. Our conversation will kick off by exploring the positive aspects of 3D concrete printing in the field of 3D concrete printing, and also in context of sustainability. Following that, we'll shift our focus to the current challenges and limitations need to be resolved, aiming to enhance the technology's sustainability and foster more positive environmental implications. Let's jump right into our discussion then. The positive side of 3D concrete printing in context of sustainability are as follows. The first one is resource efficiency and material optimization. 3D concrete printing offers significant potential for resource efficiency. It minimizes material waste by using only the necessary amount of concrete required for construction. Compared to conventional methods, which often involves excess materials and generate considerable construction waste, 3D printing optimizes material use, reducing environmental impact. Not just saving materials, but also exclusion of formwork reduces the embodied carbon dioxide or emission. The second is carbon footprint reduction. Following from the previous quotes, reducing the carbon footprint is a pivotal aspect of sustainable construction. 3D concrete techniques utilize those focusing on optimizing designs and reducing material consumption contribute to lowering CO2 emission during both construction and transportation. This aspect aligns with global efforts to mitigate climate change by curbing greenhouse gas emissions. The third point is innovation driving sustainability. Technological advancement takes an important role in enhancing sustainability in 3D concrete printing. Innovations in eco-friendly materials such as recycled aggregate usage, zero cement binder development, or improved printing methodologies that reduce the energy consumption and research into recycled materials are propelling the important propelling or the industry towards a more sustainable practices. The fourth point is environmental benefits beyond material reduction. So the environmental benefits of 3D concrete printing extend beyond reduced material usage. The technology minimizes site disturbance as it often requires less space and disturbance during construction. Moreover, innovative design can contribute to mitigating urban heat island effects and fostering more environmentally conscious urban planning. The fifth point is a social and economic impact. Sustainable construction practice through 3D concrete printing can have profound societal and economic implications. These may include advancements in affordable housing solutions, job creation in the green technology sector, and fostering sustainable development practice in both urban and rural settings. Now we can discuss a few limitations and the challenges to achieve better sustainability and positive environmental implications. The first is the full-size aggregate usage. The many experts highlight the significant impact of high mortar content on the environmental sustainability of 3D concrete printing, largely due to the use of small aggregate or a fine aggregate in the current printing processes. The challenge lies in the absence of comprehensive solutions for printing concrete with full-size aggregate up to 37.5 millimeters due to technical limitation such as a pump limitation. Current printer setup struggles to accommodate large aggregate, risking blockage in the feed pump or hose. Additionally, the material's pumpability and extrudability during its fresh states are affected. Despite these obstacles, efforts persist to develop mixtures with large aggregates, with some projects showcasing 3D concrete printing involving up to 8 millimeter aggregates, or nowadays even more. Utilizing coarser aggregates could reduce sand and cement consumption, thereby lessening the environmental impact and economic cost of 3D concrete printing. This claim stems from the understanding the OPC is the most impactful raw material in 3D CP concrete printing mixtures. However, this trajectory assumes that increasing aggregate sizes, similar to traditional concrete construction, would enhance the environmental sustainability of 3D concrete printing, disregarding the environmental and social impacts of full-size aggregate compositions. A recent project by a 3D concrete printing group like Cobalt aimed to address this issue by using locally sourced concrete with large aggregate to construct a small house. However, this choice led to high volume of concrete usage, necessitating a large nozzle dimension due to the aggregate size. While designers claim that 3D printing uses significantly less concrete than conventional construction and reduces CO2 emissions, these assertions often lack substantiating data or analysis. Without this data, determining the actual emission of a 3D concrete printing house remains unclear, unfortunately, which actually impeding the informed architectural decision regarding the incorporating of 3D concrete printing into design. The second point is recycled aggregate usage. So increasing the proportion of aggregates to cement in 3D concrete printing may indicate a decrease in environmental impact concerning embodied carbon. However, it still heavily relies on extracting virgin raw materials from the earth, which contributes to the growing challenge of materials scarcity in the architecture, engineering, and construction industry. Consequently, some researchers are exploring the potential use of recycled materials as aggregate for 3D concrete printing, ranging from recycled brick aggregates to repurposed latex and vinyl gloves. This trajectory aims to make 3D concrete printing more circular and sustainable while alleviating the strain on raw material resources. In a recent environment sustainability review of 3D concrete printing, researchers have proposed utilizing recycled aggregate as a means to mitigate environmental impacts. While acknowledging its potential, they highlight the necessity for further studies to thoroughly evaluate this approach. Interestingly, there is a notable scarcity of research examining recycled fine aggregate in 3D concrete printing, and even less on commonly used recycled coarse aggregates, in contrast to the extensive research in other material science domains. The processing of aggregates, their widespread availability, and the volume of potential recycled aggregate pose significant considerations. Researchers employ the life cycle assessment as a tool to gauge the environmental impact of recycled aggregates in concrete, which identify crucial factors like transportation distance and the measurement of functional units that significantly influence the results. While these studies focus solely on the production stage and omit the removing considerations of recycled aggregate concrete's end of life, they provoke a pertinent query for material science research. Is it more environmentally sustainable to opt for locally sourced raw aggregates or procure recycled aggregate from more distant locations? This question underscores the intricacies in understanding the environmental complexities associated with 3D concrete printing. Given that ordinary Portland cement is acknowledged for its substantial environmental impact, an additional avenue of research within 3D concrete printing explores the reduction and substitution of OPC or Portland cement with alternatives that are less environmentally impactful. Various alternatives for OPC or Portland cement have been proposed to address the embodied carbon concerns in 3D concrete printing mixtures, which are geopolymers and alkali activated materials, and fly ash slag emerges as a relatively successful placement. Researchers highlight the significant potential of supplementary cementitious material, or like sometimes called the SCM, to curtail carbon emissions to reduce virgin resources consumption in cement production, particularly beneficial for developing countries. While flash and slag have demonstrated their ability to diminish CO2 emissions in concrete production, it's worth noting that these replacements are byproducts from other unsustainable processes, and their global supply is then actually limited. A more encouraging substitute is calcined clay, which is abundantly available worldwide, and its production process is considerably less environmentally taxing than Portland cement. The calcination process demands fewer fuels because it's a lower the temperature and degree. It meets substantially less CO2 compared to clinker production, primarily due to the lower burning temperature. Yeah, as I said, like of calcinated clay compared to clinker. An LCA study based on the Cuban cement industry revealed emissions ranging from 0.25 to 0.37 kilograms CO2 per kilogram for calcined clay. In contrast, around 0.9 kilograms of CO2 per kilogram for Portland cement manufacturing. So while these figures show promise, further evaluations are imperative to determine their applicability in different geographical contexts. However, replacing Portland cement with calcined clay doesn't fully address this issue of resource scarcity, emphasizing the importance of learning from past unsustainable practices. An emerging and forward-looking alternative lies in engineered biology-based cement. Innovations like biocement, inspired by coral production, that have the potential to eliminate 1 kilogram CO2 for every kilogram of biocement used instead of Portland cement. Although this technology is still in early development, with its sole application within the architecture, engineering, and construction industry being precast tiles, its compatibility with additive manufacturing techniques remains uncertain. Overcoming these challenges and substantiating the associated figures could mark an exciting future development in the field of material science. The next point is optimization. So in contrast to other construction materials, concrete tends to have a comparatively reduced carbon footprint when standardized by volume, implying that the excessive use of concrete significantly impacts the environment. One of the central arguments supporting the sustainability of 3D concrete printing is its potential to curtail the quantity of the concrete used in construction, thereby reducing CO2 emissions and enhancing sustainability accordingly. This viewpoint is widely circulated across academic and industry discussion on 3D concrete printing. For instance, a recent promotional statement from a 3D concrete printing company asserts that their 3D printed walls with only 45% infill saves up to 55% of concrete materials compared to traditionally cast concrete walls. Simplifying this, basic straight wall element measuring 1 by 0.2 meter costed would equate to 0.2 cubic meters volume. However, employing a 30 millimeter print path to outline the wall's parameter and 45% interior infill would utilize a total material of 0.13 cubic meter, thereby saving 35% of the material. However, this calculation addresses only one aspect of material optimization and overlooks performance-based measures like acoustic and thermal properties that contribute to an element's overall environmental impacts. The reduction in material usage holds increasing importance amidst growing concerns over resource scarcity and production emissions. Digital fabrication has surfaced as the solution, expected to enhance construction sustainability by enabling more efficient structural design that place material precisely where needed. Manipulating tool parts present an opportunity to incorporate additional functionalities through intricate geometry. Some researchers propose that these complex parts could create cavities for secondary functions in 3D concrete printing columns or walls, integrating services like drainage, light, or watering for a living wall. However, the practicality of these structures remains untested concerning access and repair. Questions persist regarding potential structural impact and visual alteration if repair work necessitates breaking through the 3D concrete printing form. So an alternative approach involves adjusting tool pods to enhance thermal and acoustic or fire performance. For instance, a researcher, Aziz, proposed an optimized slab structure that embeds Helmholtz resonator within the print pod to absorb like a low frequency sound. So they also suggest that the surface roughness generated during the printing could diffuse high frequencies, though no empirical data substantiates these claims. If proven effective, this could significantly enhance 3D concrete printing's role in architectural design by reducing materials volume and the need for additional building components. The next aspect is analysis tool. Simulating the behavior of 3D concrete printing concrete poses significant challenges. Fresh concrete shows distinct characteristics, notably is its pumpability, buildability, or printability window. Of these ensuring buildability, the stability of layers upon deposition proves particularly arduous, often resulting in unexpected failure during printing. To mitigate failure rates and anticipate printed artifact behavior, several simulation and analysis tools are under development. For instance, you can use a Grasshopper plugin to model intricate 3D concrete printing geometries, enabling subsequent and final element analysis in Abacus. The aim is to predict materials behavior during printing, reducing unforeseen prototype failures, and expediting modeling. While these tools ensure precise modeling, mastering them demand time, expense, and specialized expertise. Research like Breseghello or Naboni introduced a method to visualize and simulate toolpods foreseeing the behavior of complex printed objects. This promises swifter design iterations and hints at addressing material wastage in failed prints. By minimizing unpredictable failures, this method implies a reduction in material waste during the design's prototype phase. External elements like temperature, humidity significantly influence print success, leaving the true impact on the material saving uncertain. Reinforcement stands as a significant obstacle in integrating 3D concrete printing within industries. Due to the absence of specific regulations for 3D concrete printing structures, architects and engineers navigate compliance with building codes through multiple prototype testing or by aligning their designs with static calculations typical in traditional concrete constructions. One potential remedy for this challenge involves the development of compression-only structures. Inspired by masonry-based design principles, a design tool aids in creating large-scale, unreinforced 3D concrete printing elements. This tool was demonstrated in the design of a bridge, Striatus. A collaborator endeavor presented a bridge as a model of a structure devoid of internal reinforcement or adhered elements. The lack of embedded reinforcements not only resolves the technological barriers in embedding reinforcement in a 3D concrete printing process, but also allows for rapid disassembly and potential reuse or the recycling of printed components. Designing compression-only structures allows for eliminating reinforcement from concrete, a material that significantly influences structural concrete. Advocates propose that using a single material eliminates the need for material sorting, potentially streamlining costs. They also claim that all components are designed for disassembly and reuse. However, while disassembly aligns with the circular design strategies, 3D concrete printing elements are often tailored for special purposes, raising uncertainties about their reusability or repurposing. Thank you for joining us today as we explore the fascinating aspects of sustainability and environmental implications within 3D concrete printing, as well as some challenges needs to be addressed. Remember, journey towards sustainable construction practice is ongoing and collaborative. We hope this exploration sparks further curiosity and action in adopting more sustainable practice within the construction industry. Until next time, let's continue building a greener, more sustainable future together. So thank you for your attention and bye for now.